Okay, so I hope you had a chance to look at it. This is a serial query. So that's a different, it looks the same, but it's a different problem. It's a serial query, and you see the human time was 1.9 minutes, but it looks like the query has used 2.4 minutes of time. So how is this possible? I mean, when I see this, I would always suspect parallel queries, but this is not a parallel query. You see, it's a serial query, right? And I'm gonna demo this. So let's now. I'm gonna run the same or similar query. I'm gonna actually make it the same query, and all right. So I'm gonna go to the order entry schema. I'm using swing page. So I had a monitor hint here, so that monitoring would kick in immediately. And I'm doing an index range scan through an orders table, right? And I force an index. I'm actually going through all the rows. I'm retrieving like 90% of rows, or 99. So that's why I forced some index to be used. Okay, and let's do the enterprise manager thing. So, I'm using the enterprise manager express here. So we have a query that's running. So this is now running. This is running on a bare metal machine, in the sense that this is an actual server running Linux, and you see I'm doing a lot of IOs. So I've done 300,000 IO requests already, right? And actually, if I wanna, let's geek out from the geek out session for a moment. So if I log in, if I run my snapper script, for example, just to see how many IO operations is this session doing right now. Okay, so this is my snapper script, if you don't know what it is. So I have hacking sessions about that as well. You see, we are doing 10,000 IO requests per second. See, and actually I did even more when I flushed the buffer cache. So we're doing 10,000 IO requests per second. That's gonna you not only wait for IOs, you wait for IOs, but this is gonna cause some CPU as well, because every IO request also uses CPU. Okay, so I don't really have that much of a problem here. You see, this total time is a bit longer than the duration, but let me run the same thing now on a. I'm gonna run the same thing on a VM, and it's running on a VirtualBox VM, because that's the worst in my experience for this purpose. So I'm gonna run the same query in VirtualBox. Let me. It's roughly the same data. I think it's a little less rows, but so 173 is the session. I just want to see how many IOs per second this guy is doing. It's a VM, on flash storage, but the VM causes some trouble in between. Okay. And apparently even running Snapper takes a while. So it's running rack on a laptop actually. So that's probably not a great idea. I don't know what happened here. So usually it works, right? So let me just run one more. So maybe I'm causing too much trouble here, but. Okay, so not finished. I'm not going to troubleshoot why it took longer than 5 seconds. So that's for a different day. But you see, well, because this is running on a laptop and so on, it's doing 1,000 IOs per second only, right? Okay, and now, okay, this guy is still running. Let me run a SQL monitoring report, right? So this script runs the SQL monitoring package in Oracle, it spools the output into a local file, and then it opens a browser. With the local file, right? And I guess it's again like it's a small laptop trying to run 2 nodes of rack, and that's why everything is kind of slow. Just gonna see. I'm gonna look into what is my SQL mon script itself doing. Okay, now it opened up. So, all right. So this query hasn't finished yet, but it doesn't really matter. What I want to show you here is this. So, so this is like an opposite thing to what to one of the things what I showed. So first of all, the query ran, or the query has executed for 1.6 minutes so far, and you see it hasn't really, we haven't completed any fetches yet. We actually haven't produced any rows yet, right? Because we're still going through this bunch of rows. You see we're producing hundreds of thousands of rows. We're doing hundreds of thousands of IO requests, and we're producing, we have produced 500,000 rows to this sort, which is essentially gonna just do a, it's a max order total, right? So it hasn't found out the max yet because there are still rows coming from this from under it in the tree, right? So it hasn't returned anything yet. But anyway, so that's weird. How come the actual database time spent actively in the database is twice longer than the human wall clock time since we started the query? And this is not a parallel query. And so now I'm gonna think how should I explain this? So actually, I'm gonna jump into one different slide. I'm gonna include it into the PDF as well, and I will upload that. All right, so I will add this to the slides as well. So this is basically how Oracle Wait interface works in principle. So that when, let's say that there is a physical read, you want to read something in from disk. Okay. Actually, you know what? Let me. I want to highlight this as well. Let me see if I can do it. Okay, I can do it like this. So, let's say that you want to read a block from disk. Okay. So how does Oracle Wait interface work? Or Oracle registers that, usually there are exceptions, like Fritz will tell you, but usually, just before you issue an IO, like a synchronous read request, Oracle registers that, hey, I'm doing a wait event now. That I started, it takes a timestamp, that I started a wait like DB file sequential read. When I move my mouse here, you see, well, this is DB file parallel read, actually, because it's batched IO. We are reading many blocks in with a single system call. DB file parallel read, but there is DB file sequential read. So just before Oracle issues its system call in the kernel, OS kernel level, it will take a timestamp, right? It will update VDollar session saying that, hey, I'm waiting now, and it will take a timestamp. And later on, when the wait ends, it will take another timestamp. It will update VDollar session saying that, okay, I'm not waiting anymore, therefore I must be on CPU. And it will take a timestamp. And the delta between these two timestamps will be the wait duration. It will be the elapsed time of this wait, what you see in SQL trace. SQL trace would print something out here, right, in this line, okay? But what does this have to do with our problem here? Well, let's look into this again. When we are about to start a wait, Oracle takes a timestamp, and then Oracle issues a system call to the operating system level, And now in the OS kernel level, we are using some CPU. We are going through file system layers. We are going through, logical volume layers. We are going through SCSI drivers, device drivers or things like that. There are all kinds of I/O queues nowadays. There are multiple queues, depending on the configuration. These I/O queues are protected by spin locks in the kernel. You have to take a spin lock, then you queue up something. All of this takes time. All of this takes CPU time. Oracle thinks it's already waiting, right? Oracle has registered, hey, I'm waiting now. But actually, we are burning CPU in the OS kernel level, trying to get this I/O ready. And now we submit the I/O, then we go to sleep. The OS puts us to sleep. And when the I/O finishes, then we are doing more CPU usage. Depending on, if you're using, if you're not using direct I/O, then data gets copied around and I/Os need to complete it. I/O structures need to be cleaned and completed. So there is more CPU here. So basically what this means is that Oracle thinks we slept. Let's say that this is 1 millisecond. Oracle thinks that we spent 1 millisecond sleeping, but actually 20% of that was on CPU, and another 15% was also on CPU. So Oracle thinks that we spent all this time sleeping, but actually under the hood we used CPU as well. Okay, and this really didn't matter back in the day, because when you used old spinning disks, then this took 20 milliseconds anyway, right? So spending another 200 microseconds on CPU in the context of 20 milliseconds of spinning disk wait time, that wasn't big enough. You didn't really see these anomalies. But nowadays, when you have very fast SSDs, the I/O service time might be under 100 microseconds. And then when you are on a crappy VM like I am, where every I/O submission takes hundreds of microseconds of CPU time, because different reasons, what I'm going to talk about someday, that's what you end up with. So you see, this is 1.6 minutes. If I ignore the CPU for a second, you see the wait time is 1.6 minutes plus, I guess there is like a few seconds of cluster wait time. So if I added all this together, I can actually, I could take the seconds here, 73 seconds, 3 more, 76 seconds, 79, 80 seconds. 80 seconds of wait times as Ash sees it, right? 80 seconds of wait time and 13 more. So that's like 96 seconds of time spent actively doing something in the database, as Ash says. So 96 seconds is, well, it's 1.6 minutes, right? It's close enough. Because 90 seconds is 1.5 minutes. 96 seconds is 1.6. So that's correct. And you see the Ash CPU in this case is 13. As far as Ash sees, we were on CPU 13 for 13 seconds, but and the rest of the time was waiting. But if I go into the OS level and actually ask from OS, what was my real CPU usage? User mode CPU and OS kernel mode CPU, then I get the much bigger number. So it's not 13 seconds, it's 90 something seconds. So the actual CPU, what really was used, is much bigger than Oracle thinks. And how you would sort of think about that is this. Actually, I have it on the slide as well. I just put it. Well, this is a different, that's a different thing actually. So how you can think about this visually is this, that this box, what I just highlighted, right? This is the amount of CPU consumed likely in the OS kernel level while we were in a wait event in Oracle already. So Oracle submitted an I/O, but we still used more CPU in the OS kernel level for all the processing, all the I/O processing. So this box here, we know that the CPU was used because the OS level metrics don't lie like that, right? But this CPU was used while being inside the wait event, because Oracle wait event is not only wait, it also includes any CPU service time for doing this particular IO or whatever system call we are talking about. Okay, so, and that's why I showed this first with my bare metal machine. So this is a bare metal machine which did 800,000 IOPS, not IOPS, 800,000 IO requests for this query. And you see, it's only slightly bigger. You know, if the CPU, the extra CPU, you know, which makes this total time, you know, which brings this double counting, so to speak, you know, it's not that much bigger, because this is bare metal machine. My IOs take very little CPU, right? But yeah, I'm not even going to show that, but it's but in this case, you know, if you go and run vmstat or top in the host machine, you would see a lot of kernel mode CPU usage and software interrupt CPU usage and so on. And it's all because the virtual machines, especially VirtualBox, are not very good at handling a lot of very fast I/O, right? If you're on a spinning disk, you don't notice a problem, but if you're doing concurrent I/O, you want to do a million IOPS, that's a problem. Okay. All right. So let's see if let's go through a few questions, and then we go to the execution timeline. And the execution timeline is mostly hacking session, I'll just show you a few examples. Okay. And yeah, Hoyce, you mentioned that, yeah, the CPU becomes a bottleneck because the I/O bottleneck is removed. On slow spinning disks, that's not the problem. And yes, that's exactly correct. Like Kevin Clausen says, everything is a CPU problem, right? If your storage is slow, then you're not using CPU enough because you're constantly waiting for storage. And when you suddenly upgrade to a very fast storage, then your CPU goes through the roof, but you're getting much more work done, right, per second. Because the storage is not the bottleneck anymore, you know, there is always going to be the next bottleneck, right? And it is likely going to be CPU, right? If I/O gets out of the way, then, well, what's left? CPU. Okay. All right. So, earlier when we talked about CPU here, that's actually a good point as well. You see where we had a, you know, like we only have 16 CPU cores, but we have so many more processes trying to be on CPU. I had Resource Manager disabled here, right? Of course, if Resource Manager had been enabled, then instead of this mess, this madness of constantly competing for CPU with 100 processes, that would have gone away. So you would have seen a lighter green color here, and Resource Manager would not have let more than 16 processes compete for the CPU. You know, that these peaks here up here would have turned into a Resource Manager CPU quantum wait events, right? Even though it's a scheduler, this is not the OS scheduler, this is the Oracle level scheduler essentially. And you know, when Resource Manager asks an Oracle process to go to sleep essentially, then that wait event shows up.